Good evening, everybody. Welcome to lesson 11 of our mini bootcamp series. For anyone who's joining us for the first time, my name is Deandra Ryan Moss, and I am an instructor at Lambda School. And this is our computer science mini bootcamp. So this course is a free 3-week course on just the basics of web development. So we covered at the beginning some HTML and CSS, and then we've spent basically the last 2 weeks going over JavaScript. And we're just wrapping up here. So tonight is our last lesson on JavaScript, and we'll have one more lesson tomorrow on DOM manipulation. So if you are just jumping in for the first time, I would definitely recommend you check out some of the older videos. We have them all on YouTube, and we're going to start a whole new series next month. So if you want to jump in and follow along in real time, that will be going live the first week of April. And if you don't know anything about our main curriculum at Lambda School, let me tell you a little about that. So Lambda School is an online computer science and web development immersive. So it is a 6-month program, and we get you from the point where you finish this boot camp, which is, you know, a little bit about web development, to the point where you are ready to be hired in a full-time web development position. So in that course, we go over front-end frameworks, back-end frameworks, we do a personal project, and then we go ahead and jump into some computer science topics, talking about object-oriented languages, Python, some algorithms. So it really is a thorough course that gets you ready for a real-world job. And what's extra exciting about this course is that it is de-risked, which means that you do not have to pay anything upfront if you don't want. So rather than paying our tuition upfront, which is also an option, you can sign a contract to either pay back tuition during your first 2 years on the job. So in that way, you do not have to pay us until we get you the job that you want. So once you've started your full-time over 50K computer programming job, then you pay us. And if you don't get that, then no harm, no foul. So it is on us to make sure that you are ready for the real world. Well, let's go ahead and jump into our topic for tonight. So we have been talking about JavaScript for a couple weeks now. It's getting pretty intense. Last night we covered scope and closure, and tonight we are going to jump into what is my absolute favorite topic, which is recursion. So I am very excited. Let me go ahead and share my screen, and then we can do a little review of what we learned last night and go ahead and dive into recursion. Okay, so let's talk a little bit about scope and closure, which is what we saw last night. So whenever I declare a function, I create something called a function scope. So everything I do inside of these 2 curly brackets are inside the function scope. So if I, for example, declare a variable up here, that is available in the scope. So inside the scope of this function, I can access anything in the global scope, which is to say anything that exists just outside of the function layer. So if I want to console log this number variable from inside of the function scope, that's totally fine. That's completely allowed. But scope only goes one way. So we can't do the opposite. So if instead I created a string in here and I tried console logging that outside of the function, it's not going to work. So whatever is declared inside of this function scope only exists inside of this function scope. And that can be really useful because we don't have to worry about using unique variable names. I could create another function over here, and I could still create the string variable with the same name. And it doesn't matter because once we're outside of this function scope, it's like it never existed. And we have a fresh slate once we're inside of another function scope. An interesting use of scope is something called closure, which we also talked about last night. So we learned that functions can do something pretty crazy, which is return functions. So inside of this outer function, we're returning a smaller anonymous function. And what's really cool is that while the string variable isn't accessible in the global scope out here, it is accessible inside of this inner function. So I can go ahead and console log string. I could even return string. And so that is very useful because while this variable isn't available in the global scope, we've essentially created a copy of it down here in this anonymous function. And that copy is called a closure. So if we go ahead and run my function, which we're not using that argument anywhere, so let's get rid of it. So if we run my function, it's going to create another function as its output. And let me get rid of that console log. So we'll return this inner function. And then when we run that, we get our string variable. So what's great is that we can use this technique to keep a variable kind of out of sight, inaccessible to the public in a general sense, but still be able to grab it by running this output function. So that is the idea of closure. And once again, both of these are pretty advanced JavaScript topics. So if you don't feel like an expert yet, that's totally okay. But hopefully you have the basics down because they're going to help you in understanding our next topic, which is recursion. So recursion, in the simplest sense, is calling a function inside of itself. Yes, things are getting very meta now. So and you might be like, what? I must be misunderstanding what you're saying because there's no way you could call a function inside itself, but you actually can. So let me show you how that works. I'm going to create this very basic function called recurse. And so as we know from our, actually, and let me have it console log. Recursion is pretty cool. Okay. So as we know, we've created this scope, right? Inside of this recurse function is this function scope. And anything out here is accessible inside of the scope. So if I wanted to use this variable, named variable, that's accessible. But this recurse function also exists in the global scope. So if I want, I have access to recurse inside of recurse. That's right. Inside of the declaration of this recurse function, I can call the function itself. So what is going to happen here if I call this? Well, it's going to log recursion is pretty cool, and then it's going to call itself, and then it's going to log recursion is pretty cool, and then it's going to call itself. And it seems like it might just keep doing that forever. Uh-oh. So we have just created what's called a Stack Overflow. So yeah, that useful website called Stack Overflow is named for this thing that happens in JavaScript when your code just runs forever and ever and ever, and you get this maximum call stack size exceeds error. As we see before it errored out, we logged it a bunch of times. I could keep scrolling forever, essentially, here. So what happened when I called this function is that it logged, it called itself, it popped back up here, it logged, it called itself, and there was nothing to ever tell it to stop, so it just kept going forever. So yes, this is an example of recursion, but this is not an example of how you want to use recursion because we do not like Stack Overflows. And while things like Repl.it and the console have little built-in techniques for handling Stack Overflows so that your computer doesn't explode, there's still something you generally want to avoid. So we've learned hopefully what recursion is and maybe a little bit about how recursion should not be used. And before I move on to a use case of where recursion goes right, I want to just give you a little model to examine recursion through because it is conceptually a very difficult topic. It starts to get really confusing because there's the function and there's the function call inside the function call and then the function call inside the function call inside the function call. So I like to think about it as a Russian doll. So if anyone is not familiar with Russian dolls, they're these little creepy things. My mom had a bunch of these when I was a little kid and I found them fascinating, which I think was just my brain preparing itself for recursion many years later. But Russian dolls are, they're usually like 5 or 6, maybe 7 dolls, and they look exactly the same, but each one is a little smaller, and they're all nestled inside of each other. So while they look the same, there are actually 5 copies of the doll, right? And that's how you should think about recursion. There's actually, well, in this case, infinitely many copies of recurse. But each time we call recurse, we create a new copy of the function nested inside the old one. So instead of thinking about this as just one function call, we want to think about this as, 100 or 1,000 or however many we got to before Replit told us to quit. So I'll come back to that idea a few times more throughout this lesson as we see more and more examples of recursion. So let's go ahead and get rid of this nasty example that totally broke Replit and look at a much better example. So I'm going to create a function called countdown. And it takes in a starting number and it will count down to 0. Yep, so I noticed in our question channel, Eric just asked if that was an infinite loop. Yep, exactly. So while, yeah, you can do an infinite while loop, you could do an infinite for loop. There's, yeah, essentially any loop can be, if you don't specify a moment when it should quit correctly, it's going to infinitely loop. And that's exactly what we just saw with our recursion example. Okay, back to countdown. So we have this function called countdown. It takes in a starting number, and then we want it to console log a countdown to 0. So just to give you guys a sense, if I called countdown of 5, we would want the output to be 5, 4, 3, 2, 1, 0. If we called countdown of 0, we would just want it to log 0. If we called countdown of a negative number, we wouldn't have any output because we're already below 0. We could certainly do this with a for loop, but we are going to do it with recursion instead. So I'll go ahead and jump in here. So the first thing we want this to do is log that start number, right? In the case where we called countdown of 5, the first thing it logs is 5. In this case, the first thing it logs is 0. So we'll go ahead and console log our start number. And then, of course, we could console log start -1, start -2, etc. But that's not very flexible, right? That doesn't actually take into account how start relates to 0. So this is the point where we recurse. So we're going to go ahead and call countdown, but we want to increment start. So let's break this down. This is a very simple function in the sense that there's only 2 lines, but there's a lot going on here. So what we do is we call countdown, we log the start number, and then we call it again. And now the start number is going to be less. So in this case, now start is equal to 4. So we log 4, and we call start of 3. We log 3, down to 2, down to 1, down to 0. But you might have noticed that we're going to have an infinite loop problem if we run this. Because once start gets to 0, there's nothing to really tell it to quit. It just is going to keep going and have a million negative things. And in fact, let's even, because I just love creating errors, let's go ahead and call it and see that infinite loop in action. Yep, so it just, and this is cool because we see how long it actually took. We got almost down to negative 20,000 before it quit. But at that point, it was like, all right, we're done. No more of this countdown nonsense. So we need a quit condition. Just like in our while loop and in our for loop, in our while loop, we would say while I or whatever variable is less or greater than 0, or we could put something like that in our for loop. We actually have to do that explicitly in here. And generally our quit criteria or our base case is put at the start because we want to check that first. So we know that if start is ever less than 0, we're done, right? If start is ever less than 0, we don't want to log anything. We never want to see a negative number in here. So a really simple way of telling a function that we're done is just a return statement. So I'm not sure if you've seen a return statement on its own before. Most of the time, return statements are used to return a value out. But if you want to just tell the function to quit, you can just do a return on its own. So this is our base case. We're saying, okay, once the starting number is below 0, once we're in the negatives, just return. We're done. We don't want to log anymore. But if we're equal to or greater than 0, then let's do this logic over here. So let's see how that works. Cool. Let's try a few more examples. And finally, one negative example. So that is a great little technique to use when you're playing around with code ideas in something like Repl, is just when you write a function, run it on 3 or 4 or 5 different values and make sure that it's doing everything you think it's doing. So we have created our first useful recursive function, this countdown function. And before we move on, I want to break down in perhaps painful detail what is going on here. Because, like I said, this is really simple in terms of lines of code, but there's some really subtle stuff going on here. So let's talk about what happens when I run countdown of, let's do 3. Actually, I'll do 2, even simpler. So what happens is, first we have countdown is called, start is equal to 2, right? That's pretty clear from that line of code. So this is our largest Russian doll. We have this first function call of countdown. And then within this, we check our base case. And we get false, right? 2 is definitely greater than 0. So we skip that. Then we log 2. Oops. And then we hit the recursion. So this is where it gets tough. So within this function call, we have another function call. And now start is equal to 1. So this is where the Russian doll metaphor becomes really important, because this is a totally new function call. It's nestled in the bigger one, and it has the same form, but it's different. And you can tell because all the variables within this will be equal to something different. And this is where this idea of scope comes in. Up here in this first function call, the variable start is equal to 2. In that function scope, start has that value. But in this function scope, start has a totally different value. And so using this value of start, we check our base case again, and once again it's false. We hit our console log statement and we log out 1. And then we hit our recursion. And now we are on to our third Russian doll function. So countdown is called a third time. Once again, this is a third unique scope that's being created. And start has a totally different value in here. We check our base case and see it's checking less than 0. So it's still false. And then we, of course, log 0. And then we recurse one more time. So we actually have 4 function calls in here. Now start is equal to -1. And you might be going, wait, what? I thought we never wanted negatives. Well, we don't want negatives logged, but we have to get down to negatives to trigger a base case. So now we check the base case condition, and it's true. So we return. And this is another place where I think people get really tripped up on recursion, because you might think, okay, we hit this return statement inside of our 4th function call, so it spits back out and we're done. Wrong. This is the most important subtle point of recursion that is so easy to miss. So when we return out of this function call, we're not all the way out in our global scope again. We're inside of this one here. And so what happens here is we hit the end of our function. So you don't need this because a return statement and the end of a function are exactly the same, but it's essentially as if there's a return statement down here. So now we pop back outside of this call, and we're still inside of our third function, but we return. And now we pop back out here, we return, and we pop back out here and we return, and now we're done. So we actually called this function 4 times and we returned 4 times. And that's really important to remember. Another metaphor I like to use is if any of you guys have seen the film Inception, it's really similar to that. So in Inception, they go inside a dream and then they go inside a dream, etc. And so when they're 3 dreams deep and they wake up, they're not just in the real world. They're still in that dream nested inside a dream. So if you haven't seen Inception, well, go watch it because it's a great movie, but don't worry about it. But I really come back to this idea of the Russian dolls. Like when you pop outside of this littlest doll, you're still inside the next littlest doll. You have to pop out 5 or 4 or however many times to get actually outside of the entire recursion thing. And in this example, it's maybe not so necessary to understand that, but it becomes really important as we get into more complicated recursive statements. So just to drive this point home, let me show you something pretty cool. So what in the world do you guys think is going to happen if I swap a recursive call and a console log? Might be tempting to think that this will have the same behavior, but something is going to change. So looking at our diagram here, we're going to have to move some things around, right? So we have countdown is called. We start at 2. Base case is false. That's all still valid. But now we don't log 2, right? We recurse first. Same thing in here. We're going to recurse before we log. So what happens when we run it? Now countdown has become count up. And in case this is confusing, let me break it down in this diagram here. So instead of logging 2, after the base case is checked, we recurse. Let me get rid of all these log statements. So we check, we see the base case is false. On the highest level, we recurse. Base case is still false, recurse. Base case is still false, recurse. The base case is true here, so we return and we pop back out into this function where start equals 0. So our recursion happens on line 6. So when we pop back out, we're where we left off. We're on line 7, which is where we log. So in this scope, start is equal to 0, so we're going to log 0. And then we're done and we pop back out again. In this scope, start is equal to 1. Pop back out one more time, and in this case, start is equal to 2. So because we're waiting, in the first version, we logged before we recursed, so we counted down as expected. But now we're waiting to log until we pop back out. So in this case, we're popping out in the opposite order. So we start with the smallest one, which is 0, then 1, then 2. So in this way, just by moving this one line of code, count down became count up. So that is recursion. Let's look at another example. So this time I'm going to use a sum example. So it's going to be kind of a similar format where sum will take a start value, which is a number, and we'll sum up that value all the way to 0. So if we call sum of 5, we would want 5 plus 4 plus 3 plus 2 plus 1 plus 0. Plus 0 isn't going to do anything. So we'll say we sum down to 1. If we call sum of 3, we would want 3 plus 2 plus 1. Filling. Okay, and if we called sum of, say, a negative number, it just wouldn't do anything. We'd get 0 out, basically, because we can't sum down to 0 if we're already below 0. So that is our sum function. So we can see that it's similar to the countdown function. There is this kind of element of counting down, but now we don't only want to count down, we also need to somehow keep track of how much we've summed up so far. So let's look at how we would write this. So we want our base case. As much as we love infinite loops, let's avoid them from here on out. So our base case is going to be, we could do 0 or we could do 1. I'll just do 1. So if start is less than 1, we return. And I'll say we return 0. So now that this base case is in order, let me comment this all out. Now that our base case is in order, we could try calling it on something like -8, which I showed you before. And we get a 0 out. So we're ready to deal with all these cases that are less than 1 because we've taken care of that. But if we call sum of 5, nothing happens because we haven't written any more logic. So let's fix that. So we want to make sure that we're keeping track of what we've summed up so far. So we have so we could call sum on our start value -1, but then there's going to be a problem here, right? Because now we've called sum. So for example, with putting in 5 as our start value, now we have sum of 4, but there's no way to really tell what went in, what's been in so far, right? We need to know how much we've added up already. So one cool thing we can do in JavaScript is we can add a second optional argument. So we have our start value, and then we have our, I'll do sum so far. So sum so far would be equal to start at the beginning. So let me show you a little bit of cool coding logic that you might not have seen before. So notice that when we initially call sum, we don't expect this to be defined. So what you can do is write this little nifty bit of code. So what this is saying is, if sum so far exists, just leave it alone, leave it as is. Or if it's undefined, set it to the start value. Because at the beginning, we just want 5. So now we have our sum so far, whether it's being passed in or if we're just initializing it to our start value. And then what we can do is when we recurse, and throw it in. Actually, wait a minute. I think we would want to start this at 0. Okay, yep, sorry guys. Okay, let's roll that back a minute. So if we're just starting, if this is our very first function call, we want the sum so far to be 0. And then down here, we want to add up our start value. And then we're ready to recurse. This one's a bit more complicated. And then, actually, is this how I want to do it? All right. Yep, this is what we want. All right, let's see if it works. That's 5 plus 4 plus 3. Yep, that's correct. So let me try 3. Looks good. Try another negative. Looks good. Okay. I know this is probably looking like magic right now. So I'm going to break down exactly what is going on here. What we do at the start is I might actually even rewrite this line to make it a little more explicit. So what we're saying is, if sum so far is undefined, then we want to set it equal to 0. If it's not defined, we just leave it alone. So this line up here is just kind of a sleek way of doing this, of doing exactly what I've done here. So I'll leave it with the if statement because I don't need to break your brains any more than necessary. So let's break down in painful detail what happens when I call, how about sum of 3? All right. So at the start, we have sum is called. And start is equal to 3. And sum so far is undefined, right? Because I haven't put anything in as the second parameter. Then what happens is we check this first if statement. So we want to see if this is undefined, which basically tells us this is our very first recursive call. And so what we do is, in this case, it is undefined. So we jump into this and we set sum so far equal to 0. Now we check our base case. Is start less than 1? It's not, so the base case is false. Right now we're on line 7. Now we jump down to line 11, which is where we actually do our summing. So we want to add whatever the start value is to sum so far. So sum so far now becomes equal to 3. 0 plus 3. And then, of course, we have this crazy statement. So what's cool about this example is we're not just recursing, but we're returning our recursive function. So the way to think about this is as follows. Think about it recursing before it ever returns. This line of code will execute and resolve before the return statement ever hits. So it's almost like 2 different lines. And in fact, I'll make it 2 different lines to make it extra explicit. So recursion result, and then I go ahead and return the recursion result. So logically, this is completely equivalent to how I had it before. I'm just kind of splitting it into 2 steps to make it even more obvious. So down on line 12, we first resolve our recursion. So sum is called a second time. This time start is equal to 2 as we decrement our start value. And sum so far is now, we've now passed it down from the other scope. So this is equal to 0 plus 3, 3. So as a little reminder, we're in a totally different function scope. So the only way that we have access to this variable is because we've passed it down. If we hadn't passed it down like that, then we would have no idea what the value was from the previous function call. So we have to pass things down like this in recursion. And then, okay, so we're at the start of a new function call. We check this first if statement. We skip it. Skip if statement. Then we check our next if statement, the base case. We skip our base case. And then we add things up. So now the sum so far variable is going to be added to start. So we add these 2 guys up. That gives us 5. And then we come down here and we recurse. So once again, the recursion will resolve before this is ever saved into a variable. So recurse. Sum is called. Start is equal to 1, or is equal to, now it's 5. All right, and so we're going to just do this again and again until we hit our base case, which is less than 1. We're almost there, guys. Bear with me. So we skip the first if statement, skip our base case, we do the summing. So now we're adding up 5 and 1. That gives us 6. And of course, now we recurse. So sum is called once more. Start is now equal to 0, and sum so far is equal to 6. And of course, we skip that first if statement. And then now we hit our base case. And because start is 0, the base case is true. And we are going to return sum so far. So we return 6. This becomes important now because in the last example, we were only using the return statement to just pop back out. But in this case, we're actually spitting a value back out. So this return statement isn't necessarily what we're going to get for our sum of 3. And I'll show you what I mean by that in a second. But we return this out to the previous call. So down here, let's see, where did we leave off? We left off on this line 12. So this return value from the inner function pops out and becomes recursion result. Recursion result becomes 6. And then we return 6 again. We pop back out here. And now we're on line 12 of a different function call, this next nested one. Recursion result is still 6. And we return 6. We pop back out one more time. Oops. Oops, that is not how you spell return. Recursion result becomes 6, and then we return 6. So you might be thinking to yourself, man, this is the most boring lesson I have ever seen in my life. Why did she just write the same thing 4 times in a row? The reason is because I really want to drive this point home. This is so important. Recursion result is not one variable. It is 3 different variables. It's defined 3 different times in 3 different function scopes. And it's returned 4 different times in 4 different function scopes. So this is the reason I wrote this out, even though it was tedious, is because it happens that many times. That's actually what's happening in these nested functions. So if I got rid of this return statement at the end, it would return once in here. This return statement would run, but this guy would never return. And this guy would never return. And our very final function would never return, which means that sum of 3 would be undefined. So it's really important to make sure that you're returning on every level, because when you recurse 4 times, that means there's 4 function scopes, which means 4 copies of every variable that's run and 4 return statements. You only have to write it once in the declaration, but when it actually runs, it runs 4 different times. And understanding this just becomes more and more critical as we run through. And just to run this point home even more, I'm going to go ahead and throw some console logs here. So I'll go ahead and console log at the top. All right, so now all I've done is just console logged our 2 starting parameters. So when I run this, I see that sure enough, it maps to what I've diagrammed out here, which is that we start with a start of 3, undefined, and it just keeps decrementing, and sum so far keeps incrementing as we sum everything up. Cool. So those are 2 recursion examples. What I've just shown you here, by the way, is more advanced than what you need to even do for the homework. So, but I did want to expose you to the subtlety of return statements, because return statements can be pretty tricky when it comes to recursion. But as with everything else, it just takes some practice. So one question you might be asking yourself is, okay, so why in the world would we want to count down or sum in such a freaking convoluted manner, right? This is by no means the easiest way to accomplish it. And in a sense, you'd be right, because in the real world, if I had to write a sum function, I would just write it iteratively rather than recursively. I'd do a loop, or I'd maybe use a dot reduce function, which we saw a few nights ago. That's absolutely a better way to do it than recursion. If you want to just be obnoxious and recurse all the time, your coworkers will hate you, but maybe it's fun for you. That's the kind of thing I would do, admittedly. Don't tell anyone. But the reason we're showing this to you is because it's a good way to introduce you to recursion. And as it turns out, even though what we saw tonight could be accomplished with a loop, not everything, there are some things that cannot be accomplished with a loop that you need recursion for. And the best example I have of that is tree structures. So if you think about something like if you had a JavaScript object that represented a family tree. So for example, this object that has a name, we'll do my grandfather's name, and then an array called children. And he only had one child. Oops. Which is my mom, whose name is Heidi. You guys are learning so much about my family in this video series. And then she had children. And there were 2 of us. Myself, of course. And I do not have any children. And then my brother. And he does not have any children. So this is a tree structure. It's kind of hairy to look at, but essentially we have this object which has children, which contains more of these objects, which contains children, which contains more of these objects. So it's kind of this fractal meta structure. It turns out that trying to get through this thing, like for example, if you wanted to print out, say I had a bunch of children and my brother had a bunch of children, or say we went all the way up to my great-grandparents. If you wanted to write a function that went through and pulled out all the children, a loop would be really bad for that because it's kind of this spidering structure, right? You don't really know how many children everyone's going to have. It turns out recursion is amazing for this kind of thing. Another example of a tree structure would be a decision tree. So for example, if you are writing some sort of game playing bot, like a chess bot, and each time you wanted to consider, all right, let's say rook to b6. I don't even know if that's a valid chess move or not. And then within rook to b6, you wanted to consider a bunch of other moves. And then within those moves, a bunch of other moves. And then out here, you want to say, well, what if instead we moved rook to, d7, etc. So this kind of spidering tree-like structure, loops cannot handle those very well, but recursion can. So we're not going to go into how to do that today, but I just want you to know that there is this really useful case for recursion. And there's a reason we love recursion, because it's built to handle these kind of chaotic tree-like structures that we actually end up seeing a lot. So on that note, tomorrow is the DOM, and it turns out that the DOM is a tree-like structure. So how convenient that we did recursion today. But for our homework tonight, you'll just be doing a couple of iterative tasks. So you're going to be doing a factorial, which is very similar to the sum function I did, and you're also going to be doing the Fibonacci sequence. Just wanted to remind you guys the Fibonacci sequence starts with 1 and 1, and then you sum up those. So 1 plus 1 is 2. And then you sum up the last 2, you get 3. Sum up those, you get 5. Sum up those, you get 8, etc. So if you need a little reminder of the Fibonacci sequence, I'm sure there are ample videos and articles online that'll remind you of what that is. So that is it for tonight. Another mind-boggling topic. Hopefully I've given you guys enough lenses to look through it. Hopefully I've tediously pseudo-coded out enough that you guys remember that every time you recurse, you create a whole new scope, a whole new function, a whole new set of variables, a whole new return value, because that, I think, is the most important thing to keep in mind when you're messing with recursion. So before I let you go, I do want to open this up to Slack. So if you guys have any more questions about recursion, go ahead and ask away. And as I said before, I love recursion. It's my favorite topic in the world. So please ask questions. Give me an excuse to talk about recursion for a little longer. Any questions? Okay, well, it sounds like you guys are all ready to go for the homework then. As always, we are available in Slack. If there's anything you want to privately message any of us about, go ahead. If you think you've got it, and then once you jump in, you're like, wow, this is way more crazy than I thought, just ask in Slack. We are here for you, and we want to help. Oh, it looks like someone is typing. Oh, a question about yesterday's homework. Yeah, we've got time, so go ahead and ask. I'm not seeing any follow-up about the yesterday's homework question. Okay, bear with us for a minute. I'll just pop up this creepy picture of these Russian dolls in the meantime, so they can stare into your soul while we wait. All right, so you have a question about the last, could you, I guess I can pull up the GitHub. I don't know offhand what the last question from last night was. That was 10 and let's see. Sonia, would you mind copying in which question you actually were? Oh, there it is. You know, I actually might skip this on the video tonight because I want to make sure I read through all this and give you a nice thorough answer. So I'm actually going to go ahead and close out the video, and we'll just continue this conversation in Slack for anyone who is wondering, and then everyone else can go ahead and get to it. So, all right, thank you for sticking around for the lecture tonight. I'm looking forward to our very last lecture tomorrow, though it'll be sad to see you guys go. Hopefully you're going on to the main curriculum. And thanks so much for learning about recursion with me tonight.